Why isn't vacuum energy a valuable power source yet? Imagine a force so tiny and elusive that it's everywhere yet impossible to harness. That's what vacuum energy is, an invisible, strange power lurking in empty space. It comes from quantum fluctuations, where particles and antiparticles briefly pop into existence and vanish again. Scientists say this activity happens constantly, even in the emptiest parts of the universe. But despite how fascinating it sounds, turning this into usable energy is a whole different story. First, the amount of vacuum energy in each tiny space is incredibly small. Think of it like trying to catch a whisper with a giant net. The energy is spread out so thinly across the universe that it's practically impossible to gather enough to power anything. Even if you could collect it, the energy density is so weak that it would take enormous amounts of space and effort to get a meaningful amount. Second, vacuum energy behaves differently from the fuel we're used to. It has what's called negative pressure, which actually pushes the universe to expand faster. This negative pressure stays constant even as space grows larger. That means it doesn't behave like a typical energy source that you can burn or drain. Instead, it's more like a cosmic push that's always there, not something you can tap into directly. Third, the laws of physics put strict limits on extracting vacuum energy. The rules of thermodynamics and quantum field theory tell us that you can't just take energy from nothing without consequences. To do so would break conservation laws or requiring conditions that are impossible to create. The vacuum isn't a reservoir waiting to be drained. It's a dynamic quantum state that resists straightforward harvesting. Fourth, experiments like the Casimir effect show tiny forces caused by vacuum fluctuations. But these effects are only visible at microscopic scales and requiring very delicate setups. Scaling these tiny forces up to generate usable power is a huge challenge. So far, attempts to build devices that tap into vacuum energy have either failed or produced results that are inconsistent or hard to reproduce. Fifth, the biggest puzzle is the discrepancy between theory and observation. Quantum field theory predicts an enormous vacuum energy density, so large that it should have ripped the universe apart long ago. But cosmological observations show a much smaller value. This huge mismatch, called the cosmological constant problem, shows that our understanding of vacuum energy is incomplete. Until we solve that, harnessing it remains out of reach. In the world of strange science, vacuum energy acts like a mysterious, almost supernatural force. Sometimes it seems to act like a superconductor under extreme magnetic fields or exerts a gentle push that accelerates the universe's expansion. But because of its strange properties, it's not something we can easily engineer or control. So in simple terms, vacuum energy isn't a practical power source yet because it's too weak, behaves differently from normal energy, is limited by physical laws, is hard to measure at useful scales, and is riddled with scientific puzzles. It's a cosmic mystery that keeps scientists intrigued, but for now, it remains just that. A strange and fascinating force we can observe but not yet use.